Hello, my name is Michael Wu, and I'm a senior studying computer science. I have experience in working with RC cars from the hardware to software that controls the vehicle. I also have a bit of experience in computer vision, machine learning, and other technologies.
Hello, I am Mark Shebley, senior in the EECS department, and I'm from Carlsbad, California. I'm interested in mechatronics and robotics, and I have experience in controls, signal processing, and computer vision. I will be honing in these skills in graduate school at UCLA next year, and am excited for this final project.
Hi everyone, I'm Adrian. I'm a senior and I have experience in computer vision and reinforcement learning.
Our project is attempting to compare and contrast a traditional planner versus a reinforcement learning based planner in a racing environment. For the traditional local planner, we have chosen to implement the dynamic windows approach, and for RL-based planner, we've chosen to use DDPG plus a custom LN-CNN policy.
We chose the dynamic windows approach planner as we found that other planners were not sufficient for our needs. RRT-based planners requires a really good heuristic for finding a trajectory efficiently, and this heuristic might be hard to come up with. Pure optimization-based planning is also quite slow, and then sinusoidal planners are not really practical besides doing parallel parking. To meet our purposes, we needed a planner that can help us plan, avoid obstacles, and do it quite quickly. For our purposes, we don't need to find a global trajectory since we guaranteed there's a global trajectory in a racetrack. And so we only need a local based planner, which in our case consistently avoids obstacles that might be new to the environment, which is why we chose DWA.
We want to see how a reinforcement learning based planner would perform because we think a learning based approach has certain advantages in planning in a noisy and partially observable environment. This is inspired and perhaps supported by a paper we read for this class, which uses learning for visual planning. We'd also like to see if the RL agent can run faster than traditional approaches, because it only needs to run the forward pass of its policy network once every time it makes a decision. We might be able to test different training algorithms and network architectures, but for now we're starting with DDPG and a LNCN policy.
Lastly, we'd also like to test the two algorithms on actual hardware. We have a vehicle equipped with just an NX, which is in charge of onboard computing power, Intel RealSense D435i, and a T265, which is in charge of the depth sensor and localization. We also have Arduino Bluetooth Nano Sense, which is in charge of sending command to the actual agents, and a car made by Traxxas, which is the actual car with engines and wheels. We are in progress of retrieving another one from Dr. Alan Yang, or we might just build another one ourselves.
I'll be referencing the dynamics window approach by using the words DWA. The DWA is derived from the motion dynamics, so it's good for robots operating at high speeds, like a car, in this case, and the Roar project. It only searches for velocities in the dynamic window, which consists of velocities reachable within a short time period, and in this case, it's 0.25 seconds. This is ideal in our case as our robot needs to be able to react to unforeseen circumstances and changes to the environment. Most other planners respond poorly in this case if they're using like a global planner. The dynamic window approach is designed to deal with motion dynamics of synchro drive robots, which we will have to change for our implementation since we'll probably model our car as with a bicycle model. By searching in only the dynamic window, we make this a local problem and not a global problem. The DWA approach maximizes an objective function, which consists of progress towards the goal location, forward velocity, and distance from the next obstacle. By maximizing this objective function, we take in all those factors into account in the most optimal way of moving our vehicle. This approach trades off the desire to move fast towards the goal, as well as avoid obstacles and move in the most efficient manner. The planner gives us a rotational and translational velocity, which we can use to move our vehicle. So essentially, our approach to local planning with the DWA is to find the desired motion and the direction, give steering commands, and then take into the account the limitations on acceleration. Again, this is done by maximizing the objective function and producing rotational and translational velocities, which look like segments of circles, and those are easy to check with collisions with the obstacles. The accelerations given in the paper provided were 50 centimeters per second squared and 60 degrees per second squared. This is like the limitation of how quickly we can move our vehicle plus speed it up. Additionally, each time step, our world is modeled by an obstacle field using sensory data, and this is gathered around the proximity of our vehicle. The results of our studies showed that the vehicle could reach speeds of 95 centimeters per second in less obstacle-riddled environments, but has to slow down when it's making a turn or going through a certain narrow path.
So reinforcement learning refers to a type of problems in machine learning where an agent observes an environment, takes sequential actions, and gets rewards from that environment. The agent's goal is to maximize the reward, and in our case, the actions our agent can take is to choose a waypoint. Since our agent is a planner and not a controller, it does not have control over the steering and the throttle. The reward function might be how much it has moved ahead. We haven't decided on what our reward function would eventually be, and designing it is an interesting challenge.
We have tested for the hardware accuracies. We have tested the T265 tracking camera in the Richmond Field Station. Localization is one of the most important basic functionalities that any advanced planning modules will require. And as you can see in this diagram, the result is pretty good. The three tracks in which we generated are very close together, and you can see that they belong to the same track. And as you can see in this video, this is exactly how we tested the camera.
On the RL side, we've started to get familiar with the simulation environment and began to tinker with the network architecture and reward functions.
We've also tested for D435i depth camera, performance in building occupancy map from depth map in the real world. And as you can see in the video, the performance is also pretty good. We can clearly see that each frame reflects the obstacle, and the black surface turns out to be not a deal breaker for the camera. But what we found is that we do need to increase the frame rate of obstacle detection and point cloud conversion algorithm. I plan on getting a 3D printed camera mount for dual cameras and constructing another vehicle for comparison purpose. I also plan on drive around with simple PID controller in the real world to demonstrate that the PID controller works in the real world, in which, because the local planner will simply produce the next waypoint instead of me hard driving it and then feed the algorithm the next waypoint. The local planner will output the next waypoint. And I will be also working closely with Adrian and Mark to get the two planners working in simulation.
I plan to finish the implementation of the DWA planner and write an agent that calls the planner with the ROAR simulation. I also need to choose a controller of my choice, which will probably be the one from the winners of last year's competition. Since we are not actively testing controllers in this project, we are comparing planners. Additionally, I wish to implement other traditional local planners, such as a potential field planning, and begin synchronizing this into ROAR. After we have the RL planner, we need to compare and contrast traditional planners to RL planners.
Our next step is to finish the training code, train the agent, and compare it against DWA. Hopefully it can learn something. I have no idea what to expect from the agent, and that's what makes these kind of projects fun.
We initially thought that black surface might be absorbing infrared and therefore degrade the performance of the ee435i depth camera. But after testing, we found it to be not the case. Therefore, we like to remove the gray covering that Dr. Alan Yang laid, just to make sure that the entire road is of the same color.
The ROR repo is quite dense and a little difficult to understand the structure initially. Michael is a big help to understand the structure as he has worked with ROR for a year now. More digestion time with the system is needed to understand how components work together. For the DWA planner, we need to use the dynamics of the model, as it is assumed in the paper that a robot with synchro drive is used. Our model is a car, but we can use a bicycle model to simplify things.
The biggest issue on the RL side is that the simulation environment only runs in real time, and it is quite computationally intensive. We might be able to bypass this by training on multiple simulations at the same time, but otherwise we would need to have a lot more time for training.